So now what remains to do is to take a piece of code and produce its evaluation graph. That's what we call recoding, with a metaphor of a tape recorder from the 1980s, you know, that records everything that happens. So from there on, we work with C++ code. Now, purposely in this presentation, we work only with very simplistic beginner-level C++ code, and what I will show you is that you can still implement AAD with results that I think you will find rather spectacular. Now, for a professional, efficient generic implementation, that's much more efficient, but maybe more difficult as a first read. I refer to the code that comes with the book, and the toy code that we'll be using in this presentation is on the same GitHub repo as the code of the book, and all the code that I'm going to show you on these slides has all been gathered in one file, toycode.h. So you will find it all there. So I have already commented on this, but let me repeat it. With finite differences, we compute derivatives by running evaluations repeatedly. So all we need is an executable evaluation code. We don't even need to see the source code or anything. But the complexity will be linear in the number of differentials. AAD will compute derivatives by running AD in reverse order over an evaluation graph, and therefore it's not enough to have an executable code for the evaluation. We actually need a graph to traverse. In return, we get a constant complexity in the number of differentials. So it gives us super fast differentiation of any scalar code. But to implement AAD, we need to extract an evaluation graph. We need to somehow extract and make available to the machine the sequence of calculations that we will call nodes and their dependencies that we will call edges. Okay? How can we do that? Well, there are several solutions have been implemented in practice. One is explicit evaluation graph. That's a solution implemented in TensorFlow. TensorFlow exposes a user interface, an API, whereby you can explicitly create nodes and edges. You can explicitly create an evaluation graph in TensorFlow's memory. You say, okay, when I'm going to ask you to run this calculation, you are going to take this matrix, you are going to multiply it by that matrix, then you are going to do that with a result, and so on and so forth. So you have instructions in Python, for instance, that will put nodes on the evaluation graph in TensorFlow's memory. When you're finished setting up your evaluation graph in TensorFlow's memory, you can tell TensorFlow, okay, now run the evaluation graph, give me the result, and then run it backwards to give me all the derivatives, right? So this solution is to let you, clients, explicitly build evaluation graphs. That's very nice, and that's very clever, and in particular, it's very well suited for the implementation of neural networks. But if you want to do it with your own code, that forces you to recode your entire libraries against TensorFlow. What if TensorFlow changes? TensorFlow 2.0 is about to be released, and this is a complete refactoring of TensorFlow. What if Google decides to stop TensorFlow, and after a few years it becomes obsolete? You know, it's very difficult in a bank, in particular, to make this kind of commitments towards a third-party library. And especially to have a whole financial system that is built, coded explicitly against the API of one given framework. That's very, very hard, right? So that's not what we want to do, and this is this is not what real AAD is, right? And I'm not making a judgment of value here, because actually there are many, many really good things in TensorFlow, but this is not what we want, okay? And another solution would be source transformation. So you can imagine that you write some code that reads and somewhat understands, makes sense of your evaluation code in C++, then builds the graphs and writes backward differential code automatically, right? Code that reads code and accordingly writes other code, right? Metaprogramming. Now, in general, this would be a very complex, pharaonic, specialized work, similar to writing a compiler. If you did that, what you wrote is basically a compiler, right? There's a variant where you use template metaprogramming in C++ and so-called introspection with C++ templates, and that's something that I introduced in chapter 15. But again, this is complex and quite heavy implementation. And by the way, it's been attempted to write kind of compilers with AAD incorporated, and to my knowledge, there, to date, it has not been done in a convincing way. It only supports a part of C++'s language and so on and so forth. So the alternative, and what we are going to do, is to use operator overloading in languages that support it, like C++. So just I hope you guys know a little bit about operator overloading, but let me recall that very quickly. When we have code that applies some operators like addition or multiplication or some math functions like log or square root to real numbers, which are usually represented by the double type in C++, then the corresponding operations are evaluated immediately. In computer science, we say eagerly. So say that I here initialize a double x with a value 1, a double y with a value 2. And when I run this line, double z is x plus y, what happens? Well, it's trivial, isn't it? X and y are added, and the result is put in z. Then when I run this line, it calculates the logarithm of x, and it puts the result in t. Okay, that's obvious. Now, what happens when I apply the same operators, not to doubles, but to some custom type that I decided to develop to hold real numbers instead of doubles? I will develop my own custom type, which here I call my number type, which later I will call number. And that's a custom type that I developed myself in order to hold the value of real numbers, so that I will use this type to represent real numbers instead of doubles. So what will the compiler do now when it finds my number type x and y, perhaps initialized, and it finds that it must add x and y? The compiler has no idea how to add objects of type my number type. So I need to tell the compiler how to do that. How I do that is with operator overloading. I code a special function called operator plus in C++. So it's a function that takes two my number types on the left and on the right and returns another number type. And whatever I code in this function is what will happen every time the compiler adds two guys of this number type, right? This is operator overloading. Similarly, I can overload the operator log for my number type. So I have a log function, so it's not a function from a double to a double. This one is an overloaded function from a my number type to a my number type. And same thing, when I will instruct the compiler to apply log to an object of type my number type, it will not try to call the standard log function that applies to doubles. It will call the overloaded log function for my number type. And whatever I put in this code is whatever will be executed. So you see, that gives us a lot of flexibility and a lot of freedom, because we can do pretty much what we want when mathematical operations are applied to our custom types. And what are we going to do? Well, what we need to do is remember, we need we want to establish a calculation graph. We want to establish the sequence of operations that happen in a large calculation so that we can backpropagate through it and find derivatives. Well, what we are going to do is to overload operators so that they record all operations along with their dependencies. And that recording will give us the calculation graph. So what I need to do for that? Well, obviously, I need a custom type to hold all my numbers. So for the moment, I call it my number type. And I will need a constructor from doubles because I will need to be able to initialize an object of this number type from a real number that it will be holding. Okay? I will need other things, but for the moment, I leave it here. And then I will overload my operators with something, with code that will record something. So for instance, the operator plus, I will put something that will record an addition, right? So it will record an addition, but it's not enough to know that when there's an addition that's happening. It needs an evaluation graph is not just a sequence of operations, it's a sequence of operations together with dependencies. So it also needs to know what is it that's being added. So I will record an addition between the left-hand side and the right-hand side here, right? Same thing for the logarithm, but that one has only one argument. When my overloaded operator for log will record the calculation of a logarithm over the argument, right? So what happens now? When I initialize my two variables of my number types to 1 and 2, this constructor is going to be called, and whatever I put in there will be executed. So typically, I will have a data member that will hold the number, and that will be initialized here. Okay. Then I skip. Then on the second line, I have z is equal to x plus y. What it's going to do, it's going to execute this code. So it will record an addition on the evaluation graph. When a log is executed, it will record a logarithm on the evaluation graph, etc., etc. Right? So when, for instance, this code is executed now, right? When the compiler executes this code, nothing is calculated. Nothing happens. Just let me finish this and then I'm with you in a sec. Nothing is calculated. Instead, what happens is this graph is recorded in memory. You see? We started by recording the initialization of a first number, x with value 1. Then we initialized x with value 2. Then we say that z will be an addition that applies to x and y. Then we take the log of x, so the log of x, so we record the log operation that refers to value 1. And finally, we have a result here that is the addition of the log and the result of the plus. Okay? So this code looks like a calculation code, but it doesn't calculate anything because it goes through operator overloading, so it doesn't apply the standard operators, it applies the overloaded operators, and we programmed the overloaded operators to record stuff in memory, right? So instead of executing this code, well, it registers the sequence of operations on the evaluation graph. So after it's recorded, what we can do with this sequence, it can be evaluated later. That's called lazy evaluation. Or it can be differentiated by applying AAD back to front. This is how we build the evaluation graph at runtime, by executing calculation code with a custom type for which operators are overloaded to perform recording. Yes? Good. Okay. Lazy evaluation. But it's one thing, lazy evaluation, so it's cool because that's how TensorFlow, for instance, sends stuff onto GPU efficiently. So lazy evaluation is good, but more importantly for us, once the sequence of operation is known and recorded, we can backpropagate derivatives through it and calculate all the derivatives of a calculation very efficiently. That's the main point for us in this presentation. But lazy evaluation is one of the another application. So now what I did so far, I didn't really explain you how to implement AD. Don't worry, I will be much more precise than this. At the moment, I just introduced the notion of operator overloading. So now I'm going to show you how we can implement AAD with that. And what I will introduce is what is now called the conventional implementation of AAD. So what we do in this conventional implementation is that we actually record every mathematical operation, every addition, every difference, every multiplication, division, power, logarithm, exponent. Everything, every single one is recorded on a data structure that we call the tape. Okay? It's really an evaluation graph, but where in machine learning that will be called an evaluation graph. In AAD lingo, we call it the tape. So machine learning and AAD are two different fields with two different sorts of people working on it, and each have developed their own lingo. It means the same thing, but the vocabulary is different. Here we call it tape, what we call an evaluation graph. We called adjoint differentiation, what practitioners in machine learning call backpropagation, etc. It's the same thing, it's just called different names. Now, this conventional, we call that now conventional implementation because we also know since recently how to do a cutting-edge implementation, a much faster one. And this is one that doesn't record individual operations, but records full expressions. And that's actually outside of the scope of this presentation because that does require some ninja level C++, right? Metaprogramming is the most difficult part of C++ programming. So that's a lot more involved, right? But it's worth it because empirically it results in 2 to 5 times faster code, right? And better memory management. Some people call it tape compression. If you see in research papers tape compression, that's what it means. Recording full expressions instead of recording operations one by one. Now in this presentation, I stick with the simpler conventional implementation, but know that if you're interested, when you fully understood this and you want to move towards a ninja implementation with template metaprogramming, this is fully explained in the last chapter of the book, chapter 15. And it's explained in the last chapter because it's by far the most complex thing about AAD. Okay, so for now, we record every mathematical operation involved in a calculation. Again, every calculation up to complex Monte Carlo simulations, I'm sorry I must be repeating this for the 5th time or what, is a sequence of pluses, minuses, additions, power, logarithms, square roots, etc. And we record every single one. I just make one comment that I haven't made before, and it will be an important one, is each one of these atomic building blocks, they all have either 0, 1, or 2 arguments, right? None of them has 3 arguments or more. We are going to make use of that. So I'm mentioning it now. Yes?
You mentioned that was very complex Monte Carlo simulation. Are you saying that you're applying AAD to Euler Mariana?
To what?
Euler Mariana to generate the class?
Sorry. You implemented your Monte Carlo either with a Euler scheme or with a different scheme, or with your own scheme, or with a fancy scheme developed by Jasper and Brian in 2012 or whatever. Doesn't matter. What will be differentiated is your code, not your intention. At the end of the day, it may be a Euler scheme, it may be something more complicated, but it will be a sequence of elementary operations all the same. And this is the sequence that's going to be differentiated. What you do, not what you mean. That's important. The machine doesn't know what you mean, but it knows what you do.
So maybe,
did I answer your question?
So when, for example, we have some function that is heavily optimized for a float or a double, like for example FRTB, Fourier transform.
Okay.
So if I want to do this operation overloading and I create my type,
Mm-hmm.
then this means I need to hardcode again this heavily optimized.
No,
function,
no.
How would you
If you know how to differentiate it, you don't need to record it. So there are two things in your question. First of all, there are two important elements in your question. The first one is, suppose that you use Intel's implementation. You don't have access to the source code of your function. So how can you build the evaluation graph? Well, you can't. There's no magic. It's impossible. So what you have to do then is for this third-party code, for these third-party functions, the only way is you make them into elementary building blocks. This function becomes another building blocks. Nobody says that you have to, that it can be only the standard C++ mathematical functions that can be building blocks. For instance, there's no normal distribution in C++. In finance, normal distribution is used all over the place. So we will want to make it a building block so that we don't differentiate through the implementation of a normal distribution, but we differentiate it as one building block for which we know the derivative that happens to be the normal density. It's the same thing for you in your case. You overload this function. With the knowledge of its derivative. You make it one of the building blocks. That's how you do it.
So then you may lose speed, for example, not depending on your own representation.
It depends. If you know analytically the derivative of your function, then you code it and you don't lose the speed. If you don't know it analytically, you have to do it by finite difference. So you lose the speed in the differentiation of your function, but not in the rest of the evaluation graph. So you only lose the speed in that little bit of calculation. This is the only bit that you differentiate with finite differences. All the rest flows. You see what I mean?
Yeah.
So you don't lose the complete speed. Otherwise, if you have access to the source code, of course, then you can take this source code and differentiate through it as usual.
The only example I can think of is FRTB. This would be kind of...
Yeah, there are other ones where like Intel has some, for Monte Carlo simulations, Intel has a very optimized, vectorized version of the inverse normal, for instance. That's one you may be willing to use. That's easy, yeah, because I know the derivative, don't I? Yes, I know. Hmm? You need to wrap that function with your new type. Yes, 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 yes. But as you say, if you don't have access to the source code, you only wrap it, and then you make it an individual. You make it a building block. Just that. You know what? What's your name? Yeah. Sorry. What I did with a log here, I mean, the logarithm is, I don't know the implementation of a logarithm. It depends on the standard library. It depends on the compiler. I don't care. I just overloaded it with my type, and then it will be recorded. So you can do the same thing for your functions. But you need, then it's your responsibility. You see, AAD will differentiate assemblies of building blocks, but the differentiation of the building blocks themselves is your responsibility. Yes, but it's not recommended to make it too large. Okay. Okay, so we have a sequence of operations, each one with either 0, 1, or 2 arguments. In this presentation, we focus on the simplicity of a code. I want to show you how to do that with very basic C++ code. And in particular, I will disregard efficiency, scalability, and best practice. I will just use code as simple as possible to explain the key ideas. And actually, this code does work, just not super efficiently. On the contrary, in the book, what I build is professional, scalable, efficient code in modern C++. And this is particularly important for AAD. It makes a significant difference. Well, it always makes a significant difference, but maybe slightly more for AAD than other algorithms, because of a recording overhead. For every operation you make, you need to produce a record, right? To produce a record is not completely free. It necessarily involves an overhead. And so an efficient implementation must minimize the overhead to the extreme and make recording as efficient as possible. The other thing that we started, or that I already commented about, is the vast memory consumption of AAD. We store in memory all the operations involved in a large calculation. This is a very large number of records. So estimated RAM consumptions, we estimated it both through empirical and theoretical means, and actually the estimation concurred at around 5 gigabytes per second of memory consumption, right? Even if you have enough memory in your computer, it's not advisable to traverse graphs that big in memory because of cache inefficiency. So an efficient implementation of conventional AAD is given and explained in Chapter 10, and in particular, it's all about effective custom memory management and how to record with minimum overhead, cache efficiency, and so on. And then on Chapter 13, I'm giving you techniques to mitigate this memory consumption. Basically, it's called checkpointing. I will not cover it here, and it consists in splitting your algorithm in pieces and differentiate piece by piece over a small tape and then somehow stitch the derivatives together. This is all explained in Chapter 13. The good news is that in the case of Monte Carlo simulations, it's a rather trivial particular example. All you have to do is to differentiate path by path. Then you only record the sequence of operations in one single path, and you average in the end. So in the case of Monte Carlo, it's rather trivial, but it's also a particular case of a general technique called checkpointing, an important one if you're going to implement AAD in production. And I won't have time to explain it today, but there's a dedicated chapter in the book. So now we're ready to talk about this record and tape data structure. So a record is something that stores one operation of a type y is f of x, where f is a building block. So maybe an addition, a logarithm, a square root, etc. Record must know the number and location of the 0, 1, or 2 arguments xi, right? And it needs also to calculate and store the 0, 1, or 2 partial derivatives to its arguments, so the df over dxi. There can be maybe 0, 1, or 2 of them, and these are building blocks, so we know the derivatives again, so that we can apply AD. So this is my record. A record knows how many arguments it has. It knows the location on tape. So the tape is, in this simple implementation, just a vector of records. Okay? So it knows the index on tape of the 2 arguments, index 1 and index 2, and it knows the up to 2 partial derivatives of this operation with respect to the arguments. That's it. Note that a record doesn't hold any information about what is this operation. It doesn't know, it doesn't need to know if it's an addition, a logarithm, or whatever. Once we have a partial derivatives, we don't care what it is, right? So again, a record just contains, we have one record per operation. An operation can have 0, 1, or 2 arguments. A record contains the number of arguments, the indices, the locations of the 2 arguments, and the local derivatives of this intermediate results with respect to the arguments. And we declare as a global variable, a global tape, which is a vector of this guy, a sequence of these guys. Yeah? So that's it. We have our tape object to hold the evaluation graph. Now we need to develop our custom number. So what our custom number type does, well, it needs to store its value. It needs to know what number it stores. And it needs also to know the index of a corresponding operation on tape. It needs to know for each variable when it was last calculated to what operation does it correspond on tape. Okay, and it's something that we need to code it so that we can initialize it with a value, with a real number, in order to create a record without arguments on tape, so that the initial values are also records on tape. Okay, so here it goes. So a number, its data members, it will know its value, and it will know where it's located on tape. Have a default constructor that does nothing, so that we can store it in vectors and so forth. That's a technicality. And we have a constructor with a value. So if we initialize it with a value, we set its value to the value, obviously. We add a new record to the tape, right? And we take, here I just take a reference to the newly created record so that I can fill it here. I just say that its number of arguments is 0, because this is initialized from a number. This is not the result of a calculation, so it doesn't have any arguments. This is a leaf in the calculation graph. This is an input, since it's initialized with a given number, right? And I just say that the index is the size of a tape minus 1. Why is it the size of a tape minus 1? Well, because I just created a new record on tape for this number, right? So its index on tape will be the last entry of a tape, so it's size minus 1. That's it. That's it for now for the number type. And now what we need to do is to overload all the mathematical operators. So what we need to do is actually not only record, but also evaluate and store the results, because we want to perform the calculation at the same time as we store it on tape to be able to differentiate it later. So we actually evaluate and store results as usual, but in addition, we also record the operation and its derivatives on tape. So code is evaluated and recorded at the same time. So let's have a look at the operator plus, for instance, in between two numbers, and it returns a number. So first thing I do is create a new record on tape for this addition operation. Okay? Take a reference on this newly created record so that I can so that I can fill its fields. Then I compute the results, so I have a number result, and then I say that the value of this result, so it's the value it stores, it's the value of the left-hand side plus the value of the right-hand side. And the value is always a double, so this will call the double overload, the standard plus operator, right? So this line will add these two numbers and store the result in the value of a result. So that's exactly what we want to do. Now we need to we need to reference the record on tape, so we need to know what is the location of my result on tape. Well, that will be the index of the new record that I just created for this operation. Therefore, it will be the size of a tape minus 1. Finally, I populate the record on tape. This is an addition, so it has two arguments, right? Okay. The index of the first argument, I read it from the LHS. The index of the second argument, I read it from the LHS. Both derivatives are 1, obviously. And all I have to do is to return my result. That's my operator overloading for plus, right?
What's the derivative 1?
The derivative of an addition, dx plus y over dx is equal to dx plus y over dy equal 1, no? That's the derivative of the result of the addition with respect to the left-hand side and right-hand side parameters. They're both 1. I want to say because it's the case, but you can, the derivative is the limit of finite differences as an exercise. You can just calculate by finite differences, take the limit, and I promise you will find 1.
Okay.
Okay. Yeah. No, you made me doubt. No, it's definitely one. Okay. So now we have the code for the over operators, for the over binary operators, will be exactly the same. It will be an exact copy-paste of this code. The only lines that are going to change are how I calculate the value, right? This line here, result value, and how I calculate the derivatives. The rest of the code will be absolutely identical for all the overloaded operators. So let's look at the operator minus. So the value now is the difference of the values. The partial derivatives are 1 and minus 1. Yes? Operator times, the value is the multiplication of the argument's values. The derivative of the right-hand side is the left-hand side. The derivative of the left-hand side is the right-hand side. Have the same thing for the division. Again, we know, well, these are the partial derivatives with respect to the left and the right, so the numerator and the denominator. And this is obviously the value. We have this, okay. Otherwise, the rest of the code is completely identical, yes? Now, if the code is in this toycode.h file, you can find it without the ellipses, obviously. Now, that's a technicality. You see, if you're going to write your code with this custom number type, then this custom number type must be able to do everything double does. So that's just a technicality, but your code will not compile without it. So for instance, if your calculation code contains some plus equal, minus equal, times equal, etc., well, your custom, the C++ compiler will not know how to do that with your custom type unless you tell it. In some other languages, the compiler is able to find out on itself that if you're doing plus equal, that means that you're doing a plus and that you assign the result in place, right? But in C++, you have full flexibility. Your plus equal can do something completely different if you want. On the flip side, the compiler will not do it on its own unless you tell it exactly what it needs to do when it sees a plus equal. So we need these overloaded on-class operators, and they have to be on-class on the number. So you have this unary plus something, which is nothing, obviously, and the minus something, which gives you the opposite number. And you have this plus equal, minus equal, times equal, divide equal. And here I overload it in the simplest possible way. I just say that if I call plus equal, then I add this and the RHS and put it back on this and return a reference on this. Again, a technicality, nothing important. So this was for the binary operators. Now we have the unary functions, you know, log, exponential, square root. Now the code is identical, and if anything, it is simpler because we only have one argument here. So let's look at the log. It's the same thing. When I call a logarithm with my custom type, I create a new record on tape, take a reference to it, calculate a result. So I store my value as the logarithm of the value of the argument. I say that the index will be the size of a tape, -1. So it's the index of the latest record that I just created on this line here. When I populate the record, I say that this is a function with one argument. It's the index of its argument on tape. I read it from the arg. And the derivative is 1 over the value of the argument, yes, of a log. And I return the result. And it's the same thing for the exponential, the square root, what have you. The only thing that changes is how you calculate the result and how you calculate the derivative. Okay. Now, there was a question, so this thing was already, this was already mentioned. is that you what you call building blocks are not necessarily the building blocks of a standard C++ library. These are the building blocks of your calculation code. In finance, we use Gaussian distributions all over the place. It's a good idea to make it a building block. So which means that I will have an operator overload for the Gaussian density and for the Gaussian cumulative distribution in exactly the same way as I had it for square root, exponential, log, etc. Okay? Now, the code for all these binary operators and for all these unary functions, it's completely identical. There's only line that change from operator to operator, and these are the lines that calculate values and derivatives. Now, you know that this is very poor design. If I decided to change something in the logic, I would have to consistently modify many different functions, right? That's why in the code of a book, chapters 10 and 15, we absolutely don't do that. We apply something called policy design that was promoted famously by Alexandrescu in his influential book published in 2001 to avoid duplication, but without overhead. Because what we don't want is anything virtual object oriented, because that has a runtime overhead. We don't want that. So we want to be able to do that efficiently. And that's best done with this policy design. But here in the presentation, it's simpler to stick with duplicated code. Now, as I said, another technicality, your number must do everything a double does. In particular, two numbers needs to be compared. Otherwise, if in your code you use the comparison operator, you compare two numbers represented by your custom type, the compiler wouldn't know how to do that. So you need to tell it. But that's obvious. You just compare the internal double values. Okay? But you actually need this code. Otherwise, your calculation code may not compile. And that's it. That's the AAD framework. Just with these pieces of code, you have a fully working AAD framework. So let's apply it. We have our simple recording framework. It's complete. Complete code is in the GitHub repo, and we may use it to record operations. So for instance, this is a simple implementation of a Black-Scholes function, right? We have all done it thousands of times. So to record a Black and Scholes calculation, we must call it, but with our number type, not with doubles. This is called instrumentation. So what we can do is to replace all doubles by numbers. So you see, I did a Control H, and every double here, I replace by numbers. Otherwise, the code is the same, right? That would work. It would do the job, but it's definitely not recommended. Because, first of all, I want to keep both versions. I want the possibility to calculate my Black-Scholes with doubles. So if I just want a value, I don't want any derivatives, then I don't want to record the operations because that costs me, and I don't want to pay for something that I don't use, right? So I want to keep both versions, and I certainly won't keep copies of both versions, where the only thing that changes is the type that holds real numbers. Right? Instead, I'm going to do a templated implementation. So I will make my Black-Scholes implementation templated on the type that holds real numbers. So basically, it means that I put a template class T in front, and I replace all my doubles with T. Okay? So nothing complicated about that. We can do some fancy stuff with templates, but this is very easy. In this case, template just means generic type. Now, best practice is to produce templated code in the first place. Worst case, your code, calculation code, uses doubles. Never mind, you turn it into a template with an old-fashioned Control H. It's not very hard. Okay. Now, if I want to only evaluate Black-Scholes and I don't want to record anything, then I just call it with doubles as arguments. I initialize my arguments as doubles, and then the compiler will know to call the double instantiation of Black-Scholes. So basically, it will call this function with T replaced by doubles. so it won't record anything. To evaluate and record, I call it with numbers as arguments. So if I initialize my arguments this time as numbers, then, and I call the Black-Scholes function with these arguments, then it will call the number instantiation of the same code, so it will calculate it and it will record its operations at the same time. Yeah? So what we get in the end is a tape, which is not exactly a graph, not the way we have seen it earlier, but it contains the exact same information. It contains the sequence of all the operations and their dependencies, and crucially, the local derivatives of each operation to its arguments. So operator overloading gives us a tape of all the mathematical operations that are involved in the calculation. After the execution of a template code for Black-Scholes, we get this tape in memory, right? We started by initializing our parameters, so that gives us records without arguments, where then we calculated all these guys in a sequence, right, with all the dependencies given by these arrows here. Right? And we recorded this sequence, and we recorded also all the dependencies, right, in the record object, as well as, crucially, all the local derivatives, the 0, 1, or 2 local derivatives. So that's not the same as the calculation, the evaluation graph that we have seen earlier for Black-Scholes. If you remember this one, this is not exactly the same thing as this, although it contains the exact same information. So, but here, all the calculations are neatly arranged by layer, where each layer only depends on the previous one, and we saw that this is what allows us to efficiently run backpropagation, whereas this is not quite the case here, because you see, the last calculation for C, it kind of fetches the strike a few layers back, right? So we have all the information, but it's not arranged in such a way that we can just directly run backpropagation over it. So we have two solutions here, right? We have a decision to make. We could turn our tape into a graph. We could transform this into this automatically. It has all the right information. So I could run an algorithm. It wouldn't be too difficult to code to transform the information here in this format there, right? But that would be a waste of computational resources. I don't want to do that. It would cost me to run this algorithm, because this is on Black-Scholes. This is easy. What if I have a sequence of millions of operations, right? That could cost me a lot to turn the information in a tape into an evaluation graph by layer. So instead of doing that, I'm going to do something which I think is smarter. I'm going to modify slightly the backpropagation algorithm so that we can apply it directly through the tape, rather than having to transform the tape into an evaluation graph at high computational cost so that I can run standard backpropagation. I will adjust my backpropagation algorithm so that it can be directly run throughout the tape with the same results. Okay? So this is pretty much all that remains to do. So, in order to do that, we need to maybe formalize the notions of ancestors and successors on tape. So we called our instrumented instance of our code. So we initialized some custom numbers here, called the Black-Scholes function, and because the arguments are of type number, it called the instrumented version of the Black-Scholes code, right? That evaluates the calculation and records all the operations on tape. Now, denote Fi, the operation number I recorded on tape, right? So F1000 will be the operation number 1000 on tape. That's it. So we know that it's a function of either 0, 1, or 2 arguments. We know that by the time we call this function, the arguments, they must have been previously either initialized or calculated, right? It has to be the case. So it has to be the case that the arguments are already on tape with indices lower than I. So these arguments, these 0, 1, or 2 arguments to xi with indices lower, strictly lower than I on tape, we call them the ancestors. And we call AI the set of the indices of the arguments to fi. And that will be a set of 0, 1, or 2 indices, all strictly less than I. Okay? We also denote n, small n, that's the number of inputs, so that's the number of initial inputs that don't depend on anything because there are inputs. And capital N, the total number of operations on tape, including the inputs, right? So the result will be X capital N. Yeah. So we denote xi, the result of the operation number I. So xi will be fi of the axis, the ancestor axis. And so xn, or will be equal to y, the final result that we're calculating. And note that our operator overloading, the code that we have just seen together, not only recorded all the operations, but also calculated all the local derivatives, dfi over dxj, for all the j's, for all the ancestors j of ai, and stored them on node number I. Okay? That's how we designed our derivatives code. No, did I lose you? No? Good. So this is what our tape looks like. Now we have we have seen ancestors. We can also see successors. It's just the reverse. J is a successor to I if I is an ancestor to J. So so here XA has 2 ancestors, this one and this one. This node has only 1 ancestor. The inputs have 0 ancestors. Again, any node can have either 0, 1, or 2 ancestors, which are located on the tape prior to the node. Now, we say that J is a successor to I if I is an ancestor to J. So the successors to xj are all the future nodes on tape that use xj as a parameter, as an argument, right? And these are the indices I of all the functions fi calculated after xj that use xj as an argument. So formally, sj will be a number of indices, all superior to j. And these are all the indices I superior to j, such that j is an ancestor of ai. Note that S may contain many indices, that any node can have an unlimited number of successors, maybe thousands, maybe millions of successors, although every node can have only 0, 1, or 2, certainly 2 or less ancestors, but as many successors. However, in theory, it's possible to have 0 successors, but a node doesn't have any successors, but that would reveal that this is something that you calculated and didn't use to produce the final result, right? So that would be symptomatic of a poor code structure where you calculate something and don't use it. So normally you would have at least 1 successor, and you can have as many of these as required. And yeah, so we have the ancestors, we have the successors, and then we can easily define the adjoint equation through the tape. So as usual, we denote xi bar, the adjoint of xi, so that's the derivative of the final result with respect to xi, with respect to the node I on tape. Okay? Evidently, the adjoint of xn of the final result, that's the derivative of the final result to itself, it's 1, as before. And from a direct application of a chain rule, you find that di over dxj for some j that's the sum over the successors of j. So that's the sum over all the operations that actually use the result xj as an argument of dy over dxi times dxi over dxj. That's a direct application of a general. That's why we needed this to define this notion of successors, right? So what we're saying is that the derivative of the final result with respect to this guy, that will be the sum of the derivatives of the final result to all the future guys that use this guy as an argument, times the partial derivative of these successors to xj, right? This is a direct application of a chain rule, once again. And in adjoint notation, it means that xj bar will be the sum over the successors of xj of dfi over dxj times xi bar, right? And the successors are always located on tape later than the ancestors. And we recall that all the dfi over dxj, all these guys, all these local derivatives have already been recorded, calculated and recorded on tape by our overloaded operators, right? On the successor node. So that gives us a first version of the adjoint accumulation algorithm. Adjoint satisfies a backward recursion as before. The last adjoint xn is given, it's equal to 1, and all of our adjoints are a weighted sum of future adjoints. So for all j, we have this adjoint equation here, that xj depends on the number of adjoints all located on tape after j. Hence, we can use this following, but unfortunately flawed algorithm. We start with xn equal 1, and then we traverse the tape backward. And for every j in the reverse order from n minus 1 to 1, we just accumulate the adjoint of xj from all of its successors. Okay? Just a direct implementation of this formula. But we have two problems. One is complexity. A node may have many successors to sum over. Right? What if this node has 1,000,000 of successors? To accumulate its adjoints, I would need to do a weighted sum of 1,000,000 terms, right? That can cost me. And it's impractical because the ancestors don't store the indices of the derivatives of the operations. It's the successors that store it. So the derivative of this guy over this guy is stored here, not here, right? But this is very simple. We just have to accumulate this number, to calculate this number differently. A more efficient practical means of computing the exact same numbers is to accumulate them from the successors and not from the ancestors. That's it. So it's the same thing. The last adjoint is still xn equal 1. We initialize all the other adjoints to 0. Right? And then we traverse the tape in the reverse order, but we accumulate the sum, this weighted sum. We don't accumulate it from the ancestor that receive it. We accumulate it from the different successors. So what we say is that each time we traverse the tape, and from each successor, we accumulate the partial adjoint of all of its ancestors. So we basically calculate this same sum, reversing the order in which we calculate it, if you want. So what we say is every time we hit a node, we don't look at its successors, we look at its ancestors. And by the time that we hit this node, necessarily we have already accumulated all its adjoints for what comes later, right? Because we're going in the reverse order. So by the time we hit this node, we know its adjoint, right? And so from this node, I'm going to add something to the adjoint of its ancestors. And it can have only 1, 0, 1, or 2. So I'm going to say that for every ancestor, I will add the adjoint of a successor, weighted by the partial derivative, which is stored on the node of the successor, right? And That resolves all the problems because the maximum complexity for every node is now 2. 2 operations, because a node may have up to 2 ancestors. It can't have more than 2 ancestors. So I can't have more than 2 things to do on every node. And successors, they store their ancestors and partial derivatives. So I know exactly what to do. And now I can translate this algorithm into a very simple, well, first write the steps of the algorithm and translate it into a very simple C++ code. So the algorithm is first I initialize all adjoint to 0, except the last one, the adjoint of the last result, which I initialize to 1. This is how I seed the tape. Then I repeat for I iterating backwards from node n to node 0, that iterating over the successor nodes, I'm accumulating the adjoint of the ancestor nodes from the successor nodes, as explained in the previous slides. And then once, when this iteration is complete, then I can read the differentials of the end result to all of its inputs that are by definition the adjoints of the inputs. This algorithm is called, well, many names. Reverse adjoint propagation, RAP is one of them. And what is AAD then? AAD is the sum of 2 things. A recording framework, something that records all your operations on tape, and an implementation of this algorithm. The sum of the 2 is AAD. So this is the adjoint accumulation code. So I'm not going to comment on it. It's a direct translation of this algorithm, and it's just a few lines of code. Okay? Maybe one thing I'm going to comment on is that it's supposed that the tape is readable because it's been declared as a global variable. It initializes a vector of adjoints, and it does the backward recursion, then returns all the adjoints. That's it. So let's apply it to Black-Scholes. So like before, we initialize a few arguments. We initialize the arguments of Black-Scholes of a type number. We call our templated code for Black-Scholes with these arguments, which we'll call the instrumented version of Black-Scholes. And this call will record the sequence of operations on tape. And then we can calculate adjoints. So I'm just calling my adjoint calculation code, giving it the final result, the results. What is it I want to differentiate? Okay? And that's it. And then I can read the delta, the rho, the derivative to the dividend yield. This one doesn't have a name, the vega, and so on and so forth. And you can check for yourselves that these are the correct ones. What was I going to say? Yes, so you give it the result because I don't want to assume that the result is necessarily the last thing to have been calculated. It may not be the case for whatever reason, so I'd rather give explicitly the reference to the result being differentiated to the adjoint calculator, and you see that it takes the index of this result on tape and iterates from there backward. So this is all you have to do, these 2 lines, to instrument some code, some simple code like Black-Scholes. Call, template your code on the real number representation type. Call it with your custom type. Call this reverse adjoint propagator, and read the derivatives in the results. And you're guaranteed that all the derivatives will be calculated by one single traversal of the tape. Therefore, for a cost similar to computation cost similar to one evaluation of, well, Black-Scholes in this case. So speaking of complexity, let's go back to what evaluation of a calculation. What does it mean to evaluate the calculation? Not talking about derivatives for a moment. It means that we sweep forward through the sequence of its operations, obviously. We execute every operation exactly once, therefore its complexity is capital N. Its complexity in the number of operations. The number of records that end up on tape. That should be obvious. What is the complexity of the adjoint propagation? It also sweeps through the sequence of operations, but backwards. And on each node, it executes either 0, 1, or 2 operation, depending on the number of arguments. Therefore, as advertised, the AAD calculates all n differentials in constant time, and in theory, all differentials are propagated in less than 2 times one evaluation, right? The worst case would be that every operation has 2 arguments. Therefore, for every operation in the forward propagation, you do 2 operations in the backward operation. In addition, the calculation must be evaluated and recorded first. Obviously, you need to record the operation before you can backpropagate through it. So the theoretical upper bound is 3 times one evaluation. But of course, in practice, there's recording and tape traversal overhead. So a good implementation generally produces as many differentials as you want in 4 to 10 times, right? Now you remember yesterday I gave you a presentation, I gave you a demonstration, but that was not with toy code, that was with professional code. And one evaluation took 0.8 seconds. And to produce 1,000 differential took 1.5 seconds. That's less than twice one evaluation. But there are a lot of other optimizations at play here. They're all explained in the book. One of the strongest one is called selective instrumentation. That means we don't instrument the entire calculation code, just what matters, etc., etc. This is all explained in chapter 12. In conclusion, we implemented AAD in the simplest possible manner, just scratching the surface of possibilities. The part 3, chapter 8 to 15 of the book will give you the detail of a complete implementation, but still this simplistic code, well, it just works and produces the correct values, but it's not very interesting for Black and Scholes, right, to compute 6 differentials. So in the 5-10 minutes that we have left, we will apply it to slightly bigger and more interesting problem of a barrier option in Dupere Monte Carlo. So, yeah. So in order to implement we're going to implement a very simplistic version of a Dupere simulation where local volatility again is given in the matrix and bilinearly interpolated in spot and time. But we still need the following pieces. We need a matrix class that does not exist in standard C++. We need a bilinear interpolation function, and we need a random number generator. So I don't want to comment on this, so in the following code I will just assume that this is given to you. Okay? And the code is templated on the real number representation type. So you see, it's so simple that it fits on one line. So I have a function that will give you the price of a barrier as a function of a spot, a local volatility matrix. So I have a vector of spots, a vector of times, and a matrix of local volatilities. I have some product parameters, maturity, strike, barrier. I tell it how many paths and how many time steps I have. And I have a random number generator, which I assume is given to me and produces some random numbers. So what am I going to do? Well, I'm going to loop over simulations, loop over paths. For each path, I will first generate a number of Gaussian increments from my random number generator. Yeah. Then I will apply it in a simple Euler scheme. So have an inner loop over the time steps, whereby I initialize the spot at S0, time to 0. I interpolate my volatility. So I suppose I have a 2D interpolator. That's very simple, classic boilerplate code. It's available in many places, or you can code your own. So it will interpolate in spot and time over the spots and times in my local volatility structure and give me the current local volatility. Then I increase my time by dt, and my spot, oh, did I say Euler scheme? It's a log Euler scheme, I'm sorry. It's a log Euler scheme. Which gives me, this is the SDE followed by the log of a spot in Dupere. I check, I monitor my barrier, I check if I'm still alive or not. If I'm dead, I may as well break out of a loop. And in the end, if I'm still alive, I pay the payoff of a call, a European call. And I loop over my paths, and I return my result, which is the sum of the payoffs. So I average it by normalization of the number of paths as an estimator of my expectation as usual. So I guess this is pretty self-explanatory, yes? So this is a very simplistic code. It kind of does the job. Obviously not acceptable by professional standards. First of all, it's specific to Dupere's model and an open-out call. It's absolutely not scalable. If I want to price another product, I need to copy the code and just change the line that evaluates payoff. If I want to price the same product in an other model like SLV or Heston, then I also need to copy the code and change the lines that generate the path. I will end up with many different functions implementing the same simulation logic for different couples of models and products. Before I know it, I will have thousands of these. And then if suddenly I need to modify simulation logic or I want to make it multi-threaded or whatever, I have 1,000 functions to modify. So this is obviously not viable, and I refer to chapter 6 of the book. We should tell you everything about a professional architecture for generic simulation libraries, where everything is properly encapsulated so that you can mix and match models and products at runtime. But for demonstration purposes here, we stick with a simplistic code. It's not only simplistic, it's also quite inefficient, because we all know that the key to efficient Monte Carlo code is that we want to do as much work as possible only once on initialization, so we do as little work as possible repeatedly during the simulations, right? This is really the #1 key to effective Monte Carlo code. And for example, in this code, if you run a profiler through it, you will find that most of the time is spent in the 2D interpolator. That's obvious, right? But the 2D interpolation is not necessary here, because the only thing you interpolate in spot and time, but only the spot is stochastic, time is deterministic. So what you should do is pre-interpolate in time so that you do a 1D interpolation at simulation time in spots and things like that. So you can do a lot better. Again, chapter 6 tells you how to build fully optimized code. And finally, this code is serial. It executes sequentially on one core, which is a bit criminal, especially with Monte Carlo simulations, which are quite easy to efficiently parallelize. So have chapter 3 teaches modern parallel C++, and chapter 7 builds a professional parallel simulation library. And section 12.5 instruments it with parallel AAD. But for the purpose of this demonstration, we stick with a non-so-efficient serial version. But one thing that we need to do is to smooth the barrier. Otherwise, we won't be able to differentiate it. In this code, I think I had a question about control flow, and in this code we have control flow here. And this control flow cannot be differentiated by IAD or otherwise. So we can't directly differentiate this code. We need to smooth it first, as I commented earlier. So how are we going to do this? Well, again, the full answer, if you want to fully understand smoothing, I recommend this presentation. But for the case of a barrier, we implement the well-known smooth barrier approximation. So it means that in a standard barrier, a barrier is in hard logic, a barrier is either dead or alive, right? If you fix above the barrier, you're 100% dead. If you fix below the barrier, you're 100% alive. The smooth barrier, and that creates a discontinuity. The smooth barrier is an approximation that will get rid of the discontinuity by saying, well, there is a fuzzy barrier region around the barrier, right, between the barrier minus epsilon and the barrier plus epsilon, whereby we are kind of like Schrodinger's cat, partly alive and partly dead. What does it mean for a financial product? It means that a part of a notional is dead and a part of a notional remains alive. So for instance, if I fix in the middle, I will say that I knock out 50% of the remaining notional and I continue the simulation with a 50% remaining. If I fix above the barrier plus epsilon over 2, I'm most definitely dead. I'm done. If I fix below barrier minus epsilon over 2, I'm most definitely alive, and I continue. But if I fix somewhere in between, I knock out part of my notional, but not all of it. And that's what makes it smooth and continuous and differentiable, right? And actually, all the traders I know of, all the exotic traders, they always smooth their barriers. Otherwise, they couldn't get the risks by AAD or otherwise. So, we need to adjust the code, and this is easy. I actually highlighted the small portions of the code that need adjusting for the smooth barrier. First, we need to give it an epsilon. Then, alive, instead of being a Boolean, true or false, in hard logic, it becomes a number between 1 and 0, initialized at 1, right? And then I say, if I'm above the barrier plus epsilon, I'm definitely dead. Alive goes to 0. If I'm below the barrier minus epsilon, I do nothing. Right? But if I'm between, I multiply my alive by an interpolation between the barrier minus epsilon and the barrier plus epsilon, and I knock out part of the notional. And in the end, I deliver my European call, but on the fraction of a notional that's still alive. That's it. So now I have a smooth barrier. I can differentiate it. And how do we differentiate it? We differentiate it just in exactly the same way that we did with Black-Scholes. We initialize all the inputs as numbers, and remember that also records them on tape. Then we call our templated evaluation code, instantiated with a number type. That will perform the evaluation and record the operations on tape. Then we call our propagate agent routine to propagate all the agents. And finally, pick the differentials as the agent of the parameters. That's it, 5 minutes. This is how it's done. So one, I initialize the inputs. Some of my inputs are vectors, some of them are matrices now, so I have to do it in a loop. Number two, I call my duper function, instrumented with inputs represented by numbers that will record them on tape, that will carry the calculation, but also record it on tape. And I call this routine that we coded together, called calculator joins. And all I have to do is to pick the results. And I know that I will have my all my derivatives for an evaluation cost that's up to 3 times one evaluation of Dupier, plus obviously the traversal cost and the recording cost. And what happens when I run this code? The computer runs out of memory and crashes. Of course, even with 100,000 paths, we're consuming an insane amount of RAM. It's not possible, it will not work. And even on a computer with enough memory, that would be cache inefficient. Fortunately, the solution in this case is completely trivial. Instead of differentiating the whole Monte Carlo, differentiate it in mini batches of, say, 1,000 paths each. That's it. And average in the end. And don't forget to wipe the tape in between the mini batches, because this is the whole point, right? To mitigate memory consumption. The average of differentials is the differential of the average, so we will get the exact same result while reducing memory footprint to operations recorded over 1,000 paths. And if we choose to use mini batches of size 1, So one path, differentiate one path at a time. This is a well-known algorithm called pathwise differentiation. This is actually what we generally apply in production. And this is also a particular and simple case of a general checkpointing algorithm, which is important due to memory consumption with AAD and fully explained in chapter 13. And this is the solution in code, right? We differentiate in mini batches, and in the end, average over the mini batches. And that's it. And the performance, I won't have time to show you, but it's with 100,000 paths, 156 times steps, it will take you 7 seconds to calculate the 1,000 differentials of Dupere, right? This is very, very remarkable result for such a simplistic code, right? 15 years ago, the best, most professional quants in the world could not do it in less than 15 minutes. So this is very remarkable result. And you can try it yourself with a toy code in the repo. This being said, if you compare to the professional code is 8 times faster in serial mode. So in parallel mode on this little laptop, it's 2 times faster. So there is still scope to do it a lot better. But still, most of the benefits of AAD you get even with such a simplistic code. Thank you very much for your attention. I really have to run now.